All right, now we need to learn the 24-hour motions in the sky, the reason and why things rise in the east and set in the west, and how exactly things move from the sky. So there's our next goal, 24-hour motion in the sky. Now the reason why things move through the sky over the course of 24 hours, why they rise in the east and they set in the west is clear. Well, that's due to the Earth's rotation. Due to Earth's rotation. The Earth spins on its axis once every 24 hours, and therefore things move across the sky. Not just the sun, but the moon rises in the east, sets in the west. The stars, lots of stars rise in the east, set in the west too. So this is a constant, ongoing sort of motion. However, even if we don't know, we go back a few hundred years, even if we don't know exactly why things move in this way, understanding this motion is still important and was known by everyone until about 100 years ago, before the electric light and television and all that. Everybody looked at the night sky all the time, and so everybody knew that. So we're kind of going to be catching up to what the rest of the human race knew 100 years or more ago. So here's, usually at this point, I ask a question and I say, okay, suppose it's 6 p.m. It's wintertime, so it's dark, and you see a star which is out there just rising over the eastern horizon, directly 100% due east at 6 p.m. Where will that star be 6 hours later? 12 hours later. And when I ask that question, usually the answer someone gives is they say, well, let's see, okay, if something rises in the east, it will come straight up out of the directly east, it will go directly overhead, and it will set directly west. And that's wrong. That's not correct. That's not how the stars move, at least here in the continental U.S. That is how stars would move if you were down on the equator, but only on the equator is that's how stars would move. So, if a star rises due east, it will not go straight overhead. It will not go directly overhead. Directly overhead is the zenith, the point directly 100% straight over your head, and that is not where that star will go. To figure that out and to understand why and how everything moves, let's think for a minute. The motion of things through the sky is a result of the Earth spinning, the Earth's rotation. Now if you spin around a few times, here, like this. If I spin around, this makes everything move in circles around me, except for one point on the ceiling directly above me and one point on the floor directly below me. 2 points aligned with my axis of rotation. As I spin, those points do not seem to be moving from my perspective, but everything else is. Everything else moves in circles round and round those two fixed, unmoving points. One on the ceiling, one on the floor, exactly aligned with the Earth's axis of rotation. And so that's how we get this apparent motion, this apparent 24-hour motion due to the Earth spinning. Now, just through blind luck, at this point in history, at this point in the Earth's history, there happens to be a nice bright star which is lined up almost perfectly with the Earth's northern axis of rotation. It's within a degree of that. That's the North Star Polaris. The North Star Polaris is not the brightest star in the sky, and it's not the most interesting for a variety of reasons, but it's the one star in the sky that never moves, no matter what time it is, early in the evening, early in the morning, late at night, whenever it is, summer, winter, anytime. If it's dark and the stars are out, you will find the North Star Polaris in exactly the same location. The North Star Polaris never moves. Whether it's early, late, evening, morning, early, late, evening, morning, summer, winter, because it just happens to be, through luck, just happens to be within 1 degree of the actual pointing direction of the Earth's axis of rotation, it doesn't move. It stays there and moves around less than 1 degree as it goes around that point. So that's the one star in the sky that never moves, and then all the other stars in the sky move in circles around it. Because, okay, we're spinning, and so it makes everything look like they're moving circles around it. So, the North Star Polaris is the one star in the sky that never moves. It's exactly at the same position in the sky, and all other stars move in circles around it. Now the location of Polaris depends on your latitude. So if you're, so we're here in the continental U.S., so it's roughly up there in the sky. If I'm in Montana, well, let's see, in Montana I'm at 46 degrees north latitude, so the North Star is 46 degrees above the northern horizon. If I'm in Colorado at 40 degrees north latitude, well, it's 40 degrees above the northern horizon. So the position varies with latitude. If I were to walk all the way up to the North Pole, it would be directly overhead. If I walk all the way south to the equator, it would sink all the way down and sit just right on that horizon. So the angle between the North Star Polaris and the horizon tells you what your latitude is. And all other stars are moving in circles around it, constantly moving in circles around it. And the idea of circles is, I mean circles in the mathematical sense. A circle is the set of points which are all the same distance from some center point. So if I draw a circle, if I could draw it well, then every single point on this circle, every spoke of this circle, every radius of this circle would be exactly the same distance. And so what that means is that as every star moves over the course of 24 hours, its distance to Polaris must not change. It always holds exactly the same distance to Polaris. If it's, I don't know, 60 degrees away from Polaris today, then it is always 60 degrees away from Polaris. And as it moves through the night and the evening and the early morning and everything, it is always exactly 60 degrees away from Polaris. All other stars move in circles around it, meaning Polaris, which means the distance between them and Polaris does not change. Distance from a star to Polaris never changes. As it moves throughout the course of a night, it does not change. And so that's why that star that rises due east can't go straight overhead. Think about it. There's Polaris. There's that star rising overhead. So I'm here in Montana, about 46 degrees north latitude. I'm pointing right at Polaris right now. There's this star rising due east. If that star were to come up, okay, so due east, look at that, that's 90 degrees, that's a right angle there. If that star were to come up straight overhead, that's not 90 degrees, that's, if straight overhead, about a 45 degree angle, half of 90. That's not a circle. If that star were to move closer to Polaris, forget about it. Well, no, that doesn't work. That's not how spinning motion makes things appear to move through the sky. So it can't move straight overhead. It must maintain that 90 degree angle at all times. So as it rises up, it must move to the south. It must come up at an angle to the south in order to maintain that 90 degree angle. So when that star rises directly due east, it doesn't come straight up. It comes at an angle to the south and ends up high in the southern sky. That's where it climaxes. It's at its highest point, and then goes over, and it does set directly due west. So, in order to move in circles around Polaris, a star must maintain a fixed distance from Polaris, never getting closer to Polaris, never getting farther from Polaris, maintaining that different distance. So what that means is a star which rises due east at, say, 6 p.m. It's wintertime, it's dark at 6 p.m. I see that bright star rising 100% exactly due east at 6 p.m. What happens at 6 p.m.? Well, it climaxes high in the southern sky. 6 hours later at 12 a.m. at midnight. Where in the southern sky? Well, about 45 degrees roughly away from that southern horizon. So about halfway between the southern horizon and the zenith straight overhead. And then it sets perfectly due west at 6 a.m. So that's how that star moves. Now let's think about another star. Let's see. Okay. What if I have a star rises south of east? South of east. If a star rises south of east, well, let's figure out what the angle is, because that's the angle that needs to be constant. There's Polaris. Okay, there's east, so south of east has got to be somewhere over there. And, ooh, look at that. That's an obtuse angle. It's more than 90 degrees. So it has to always maintain that obtuse angle. So it rises up in the south. Ooh, it's going to be very low in the southern sky. It can't be 90 degrees. It can't be less than 90 degrees. It must be an obtuse angle more than 90 degrees. So so this star that rises south of east comes up very low in the southern sky, and then, maintaining the same angle, sets south of west. A star rises south of east. It climaxes low in the south, it sets south of west. Interesting. Okay, now I'm going to give you the tough question, the killer question. I love to ask this in different classes. Just suppose I go out, it's 6 p.m. If you can understand this one, you got everything. It's 6 p.m. and there's a star just sitting right over the northern horizon. Star is just over the northern horizon. Here's the killer question. 6 a.m., 12 hours later, where will that same star be? 6 a.m., where? In real classes, I love asking this question. I ask it about half the class, and everybody gets the answer wrong because it's a tough question. Unless you think about the idea. The key idea is that everything moves in a circle, appears to move in a circle around Polaris, one circle every 24 hours. This is 12 hours later, so it's got to move in a half circle. It's going to move in a half circle around Polaris, and its distance from Polaris doesn't change. It must be the same distance away from Polaris, the same distance away from Polaris 12 hours later, but in the opposite direction. Well, what's the angle from that thing to Polaris? There's Polaris, right there up there, 46 degrees above the northern horizon. I'm in Montana. There's that star right over the northern horizon. And so what's that angle? Oh, it's about a 45-degree angle. So right now that star is 45 degrees below Polaris. So 12 hours later, that same star must be about 45 degrees above Polaris. 45 degrees above Polaris. There's Polaris, 45 degrees above Polaris. Ladies and gentlemen, that star is straight overhead. That star is directly overhead at the zenith. Where is the star? At the zenith. Directly overhead. Now that's crazy. Nobody ever gets that one the first time. So here's the deal. There's Polaris, 46 degrees above the northern horizon. There's that one star about 45 degrees below it. As it moves in a circle, it comes up, maintaining that angle. And so there it is, about 45 degrees to the right of Polaris. Okay, so it's high in the northeastern sky. It comes over. There it is, directly overhead. So that's 12 hours later. A few hours after that, that star's going to come down and be high in the southwestern sky. And then 24 hours later, it will be directly over that northern horizon again. And so this star is what, this star never rises and this star never sets. A star that never rises or sets is called a circumpolar star. A circumpolar. A star that never rises or sets. A star that never rises or sets is called a circumpolar star. It just goes in circles around Polaris. And those circles around Polaris are not big enough to let it get below the horizon. I mean, these stars that rise and set, well, they're moving in circles around Polaris too. It's just that their circles are so big, it causes them to duck below the horizon. But these stars close to Polaris, within 40 degrees or so of Polaris, are so close to it that as they move in circles around Polaris, as they move in their counterclockwise circles around Polaris, well, then they never get below the horizon. That's the Big Dipper. If you're here in the United States and it's dark and it's not cloudy, you will see the Big Dipper. It's always in the sky. Its circles around the North Star aren't big enough to let it duck below the horizon. So you just go round and round and round, and then you will always see the Big Dipper if it's dark, and then it moves in circles around it. There we go. Cool. That is a quick introduction to how things move through the night sky, and these patterns are followed by the sun, the moon, the stars, the planets. Everything out in the heavens moves in this way as a result of the Earth's 24-hour spin.